Good morning. All right. This semester, I'm gonna post the solution for the homeworks. So after you submit your homeworks, and the TA is gonna grade that, I will post the solution on the Canvas. You can check it out. But if you have any question about any homework problem, you can ask me at the beginning of class. I can work on that. All right. Let's continue the lecture. So we are on chapter 3. We are talking about economic equivalence. So let's start with doing this class activity. The question is, do you prefer to have $1,000 today or 1102 2 years from now? So this is $1,000 today or $1102 2 years from now. Answer this question with these three different interest rates. Is that clear? What I'm asking. If the money didn't have any time value, you would prefer this one. It's greater than 1,000. But since money has time value, you cannot compare the money which they occur at a different time. Number 34. Just work on the first one. 4%. What do you think? Okay.
Just the first one.
Just for 4%. So what are those numbers?
That's the 4% added to the $1,000.
Okay.
Up to 1,000. That's the 1,000.
This is for the second year.
It's for the second year. I'm not sure.
Okay. Thank you. 26, number 26, Mike.
I said that,
For the first one.
yeah, I said that it would not be better to get the $1,000 right off the bat for the first one.
So it means 1102 is better.
Yeah.
And how did you come out with this?
We used F equal to P times 1 plus I to N. And then with that at 4%, it only came out to be 1081.6.
4%. It's gonna be
1081.6.
1081.
And that's plus. So.
Alright, for the first one, since these two they don't occur at the same time, we should either move $1,000 to the second year, then compare these two values, or move this guy to the present time and compare 1,000 with that. So Michael did the first thing, so he just moved 1,000 to second year. So we are gonna use future value is gonna be present value times 1 plus I, whatever interest rate, power n, which is 2. So n I is 4%, 1 plus 4.04, power 2 times 1,000, it's gonna give us 1,000 times 1 plus power 2, 1081.6. So this is equivalent $1081 versus 1102. So it's greater than 1081. So you prefer this cash flow diagram. So at this interest rate, you prefer 1102. Do the same thing for this. Future value is going to be P1 plus 0.05 power 2 equals to 1,000 times 1.05 power 2. $1102, almost $1102. So for this one, you will get $1102. I know that it has some digit there, but the point for this problem was I just wanted to get same value, so I assume that these two are the same. So for 5% interest rate, there is no preference between $1,000 today or 1102 2 years from now. So they are equivalent. And if you choose 7%, you will get 1144.9, almost $1145. So 1145 versus 1102. It's greater than this, so you prefer this one. So as you see with with changing the interest rate, we will get the different results. So comparing the cash flow diagram depends on the interest rate that you are calculating. Any question on this? All right. And now let's talk about the compounding term on interests. So far, the interest rate that we have seen, they will be compounded yearly. So you deposit $500 in an account which pays you 6% compounded yearly for 3 years. The question is how much you will get at the end of the third year. I'm gonna work on this class activity. So you deposit $500. After 3 years, you would like to know how much you can withdraw or how much you have in your account. The point in this problem is 6% compounded yearly. So the bank is gonna pay you 6% compounded yearly. Compounded yearly means if you keep your money in the account, after 1 year, it's gonna pay you 6%. So this is the typical interest rate that we are familiar with that. So future value would be P times 1 plus 6% power 3, because we kept the money in the account for 3 years, 1, 2, 3. We can find 500 times 1.06 power 3. It's going to be $595. So next time the bank says, I'm still paying you 6% per year, but it's compounded, not yearly, quarterly. Every season, I will calculate the interest rate. This is the meaning of compounding quarterly. After 3 months, they calculate the interest, they put it in your account, and then they go to the second period of time, which is going to be 6 months from today, and then they calculate the interest for that and put it on your account. Then they go to the third quarter, and they're going to do it for the last quarter as well. Still, they announce that the interest rate is 6%, but the compounding term is different. We call this interest rate nominal interest rate. We label that with R. So whenever the compounding term is different than year, the interest rate which has been announced by the bank or credit card company or the project is called nominal interest rate. Now, if the bank pays 6% per year compounded quarterly, if I ask you what is the interest per quarter. What would be the interest per quarter? 1.6%. We have 4 quarters, 4 periods of time per year. How do I know we have 4? Because it's compounded quarterly. So we have 4 compounding terms, or 4 periods of time compounding terms. So 6% dividing by 4 is going to be 1.25%. We call this by, say it again?
No, it should be 1.5. Yeah.
Thank you, yes. It should be 1.5. 1.5% per quarter. We call, we call that with I. I is 1.5%. We call it effective interest rate per, not per year, per compounding term. So for year 1, we are going to have 4 periods of time, 4 compounding term, and in each period of time, interest rate is 1.5%. Now, if I want to know how much money can I have in the account if it's compounding quarterly, I can say 3 years. 3 years has 12 quarters. Each year has 4 quarters. We are going to have 12 periods of time. Now, instead of 3, I'm assuming we have 12 periods of time, but this time each period of time is quarter. So 3 years or 12 quarters. But the difference between this one and the 3 years is the interest rate, the effective interest rate is 1.5%. Now, if I have $500 in the account, which pays me 1.5% per quarter or per period of time, how much money can I get after 12? We know how to calculate that. F would be P times 1 plus I power n. P is 500, I is 1.5%, 1.5 divided by 100. However, how many periods of time do we have? 12. Then I can get F. $500 times 1 plus 1.5 dividing by 100 power 12. Almost 597.8, almost $598. So if the compounding term is 3%, but compounding yearly, 6% compounding yearly, I can get $595. but if it changed to the same interest rate, but this time compounding quarterly, I can get $598. Why it's different? Because in compounding quarterly, the bank is gonna pay the interest every quarter, and that interest is gonna be added to the account, and for the future, it's gonna get the benefits. Make sense? Yes.
Where did the 100 come from? On the bottom there?
1.5%. It's a 1.5%, so I put at 0.0015. So I defined R when interest rate is given per year, but compounding term is different than year because it's nominal interest rate. I defined I, effective interest rate per compounding term. I defined M, number of compounding periods per year. How many compounding terms or periods do we have in per year? In this problem, we have 4. So you can see what would be the relation between R and I and M. I would be R dividing by M. 6% divided by the number of periods per year, I can get the effective interest rate per compounding term. Now, the last term that I would like to calculate is effective interest rate. We would like to know what would be the effective interest rate that this bank is gonna pay us. We deposit $500, we could get $598. So F would be P times 1 plus, I label that with IA, power 3. So we could have $598 in the account after 3 years by having $500 deposit in the account. What would be the interest rate which makes it possible? So 598 dividing by 500 equals to 1 plus IA power 3. 598 dividing by 595 power 1 over 3 equals to 1 plus IA, and IA would be 1 this minus 1.
Shouldn't it still be the 500 on the bottom?
Yes, thank you. 500, yes. Thanks for catching. So 598 dividing by 500 power 1 over third minus 1. 0.0615. IA would be 0.0615 or 6.15% IA. So this bank is gonna pay us effective interest rate of 6.50. Make sense? Yes.
Where did the A come from
Which term?
again? The
8.
The A.
Oh, A, or sorry. A, I just labeled, I'm gonna have different parameters. I define R as a nominal interest rate when we have compounding term different than year. I define I as the effective interest rate per compounding term, since I want to have different term than I use IA. So the credit card company, they are saying that they are charging you 19%. This, for example, the 19% that they say, it's nominal interest rate, but the effective or the real interest rate that you will be charged is totally different than 19%, because the compounding term, you should look at the condition, typically it's going to be daily. Here it was quarterly and 6% change to 6.15. We will see later if it changed to daily, weekly, or continuously, how can we get the effective interest rate. Any question so far? It's a make sure that you follow the steps that I did to get this number. Any question so far? Now, what I'm gonna do, I'm gonna find relation between R, nominal interest rate, I, effective interest rate per compounding term, and number of periods per year, and effective interest rate. How can I calculate effective interest rate? How can I calculate fees? By knowing these three terms. This is what I'm gonna do. Good? Suppose you want to invest $1 in the account, which pays you R% as a nominal interest rate. So nominal interest rate is R%. We have M number of compounding terms or periods per year. And you deposit $1. $1. After 1 year, you want to know how much you can withdraw. So we are looking for F. So since the nominal interest rate is R and the number of compounding terms per year is M, the effective interest rate per compounding term is R over M. So at each period of time, the bank is gonna pay us I%. Now, how many terms do we have per year? We have M. So I can find future value by multiplying P times 1 plus I power number of periods, which is M. So how much money did we deposit in the account? $1. What is the interest rate per compounding term? Per compounding term, the bank is gonna give us R over M. And how many terms for how many periods of time we kept the money? M. So this is the money that we can get from the bank after 1 year. So 1 times this is gonna be 1 plus R over M power M. Now, if you want to find the effective interest rate, you deposit $1, you withdraw this value. The effective interest rate over 1 year is gonna be future value 1 plus R over M power M minus present value, the money that you put in the account, dividing by the money that you put in the account at the beginning. So it's gonna change to 1 plus R over M power M minus 1 divided by 1 is gonna be this. So I can write the effective interest rate is gonna be this. So we have 4 terms. R, usually you are given with this when you go to the bank to get a mortgage or get loan or lease a car, you are given with R. The financial institutes, they are required to announce the nominal interest rate to their customers. So you should know the R. But the thing that is important for you is the effective or the actual interest rate that you will be charged over the periods of loan, mortgage, or if you invest your money, you want to know how much would be the effective interest rate. So this is how you can get the effective interest rate as a function of nominal interest rate, number of periods per year, and IA can be calculated. But I can tell you it's one of the topics that I have seen that the students have had some challenge or problems with that. So make sure that you understand that. All right, let me solve some. It's a the problem. It says that if I give you $50 today, I get $60 back at the end of the week. So it means I per week or actual or effective interest per week is gonna be $60, the future value that I should pay minus the money that I borrowed dividing by 50. So 60 minus 50, 10 dividing by 50, it's gonna be 0.2 or 20% per week. If this is the condition, then the interest rate per week is 20%. If I ask you what would be the R, just look at this equation, or if you should know the concept. So R would be, you have 52 weeks. Each week has 20% or 0.2. So the nominal interest rate is gonna be 1040%. So the nominal interest rate is 1040%. Now I would like to know if I borrow the money at the beginning, $50, how much do I owe at the end of first year if the interest rate is 1040 with the nominal interest? So interest rate per week is this one. So future value would be present value times 1 plus interest rate per week is 20%, 0.2. How many weeks do we have per year? 52. $50 times 1.2 power 52. So if you borrow $50 with this condition, $50 times 1 plus 0.2 power 52. 6.55 times 10 power 5. 1, 2, 3, 4, 5. $65,230. So if you borrow $50 at the end of the year with this condition, you owe $655,000. So, and this is how we can calculate that. If I ask you find the effective interest rate, IA would be 1 plus R over M, which is 0.2 power 52 minus 1. So we would like to know how much, what would be the percentage that we will be charged. $1,310,400%. If you calculate this. Any question so far? All right. The other way that you can get this money, this number is after you calculate this, now you know the effective interest rate per year. Per year. So you can say F would be P, which is 50 times 1 plus IA power 1. 1 year is the effective interest, the number of years. So just plug in I here, multiply by 50, you will get the same number. You will get the same number. So, how many periods of time do we have if we have, if we consider compounding term continuously? If it's daily, it's gonna be 365. If it's weekly, it's gonna be 52. If it's continuously, it's gonna be infinite. Continuously, you will get so then, if you calculate the effective interest rate, IA equals to 1 plus R, M is infinite value, power infinite value, you will get this. We can show, but we don't do it in the class, the process. The limit of this, because here it goes to the 0 power infinite value, 1 plus 0 power infinite value. We should get the Haskell rules. So we can see that it's gonna, the effective interest is gonna change to E power R minus 1. R is the nominal interest rate and 1 is the number. So for continuous compounding term, this is valid. And this table just look at the first column. I have a nominal interest rate. The bank says the interest rate is 1%, 2%, 6%, 8%. If they compounding yearly, these two columns would be the same. There is no difference between the effective and nominal. But for different compounding terms, you can see, you can compare the values. 1% is gonna change to 1.005 if you compound this continuously. And 25% is gonna change to 28.4 if you compound continuously. And how can we calculate this? For example, for 25%, e power 0.25 minus 1 is going to be 0.2840. This equation, you are familiar with the single payment compound formula. So F equals to P times F over P Rn. This is the equation. You can just simply plug in this if you have continuously compounding term. IA is going to be E power R minus 1. We can cancel out 1 and you will get P times E power R times F. And vice versa. If you are given with the P, you want to find F, P would be F dividing by this. Dividing by this means negative on top. We call it single payment present force formula. So just let me work on this problem. The question is, how long will it take to double the money if the account pays 10% nominal interest compounding continuously? So 0 n. We want to deposit P, but we want to withdraw 2 times P. Future value should be double. So F would be P times E power Rn. F is 2P equals to P times E power Rn, because we want to double the future value. So you can cancel out P. 2 would be E power R. R is 0.1 times N. So we are looking for N. Ln of 2 equals to ln of E power 0.1 times N, or log, whatever you like, you can log. Ln of 2 equals to 0.1 times N. N would be ln of 2 dividing by 0.1. So ln of 2 dividing by 0.1, it's almost 7 years. You should keep the money in this account to get the double. Good? Any questions so far? Alright, now let's in chapter 3 we learned about equivalence for single payment. when we had a single payment here, P, we learned what would be the equivalent value n years later at the interest rate of I. We learned about that. But in this chapter, we will learn about the equivalence of repeated cash flow. What do I mean by repeated cash flow? When you go to get mortgage to buy a house, so for example, you are asking for 300K for the mortgage, and the bank is gonna calculate your monthly payment, and it's gonna be, for example, $1,400. So if you want to draw for 30 years, if you want to draw the cash flow diagram for your payment, you are gonna pay every month. So 30 months times 12 is gonna be 360. So the total periods of payment is 360 months. So it's gonna start from end of first month, 1,400, and you are gonna repeat this for the second time, third month, fourth month, fifth month, all the way to end of year 30. So as you see, you have repeated cash flow, you have repeated single payment. You just repeat the same amount over the time. Or if you lease a car, you have the same things. You are repeating something. So we would like to know what would be the equivalence value of this. What would be the present value or future value of this repeated cash flow? This is one thing that we are gonna learn in this chapter. The other things we learn about the arithmetic gradient. We will talk about that, geometric and some other things. And at the end of chapter, we will learn about some commands that we can use in the Excel to do the calculation. Alright, I will post the homework on Canvas and I will collect homework.